Hello everyone. Here we have a problem. We have a continuous beam, and that continuous beam we have to analyze by using MDM, moment distribution method. Moment distribution method is one of the displacement method, and in any displacement method, if you are analyzing by displacement method, the very first step is to find fixed end moment, FEM, fixed end moment. And fixed end moment depends on the loading applied on the member. You see, here we have a continuous beam AB, BC and CD. AB is having no load on the member, BC is having UDL over the entire span, and CD is having point load at the center. So FEM we have to calculate for the members. MF AB equal to MF BA equal to 0, because there is no load on member AB, hence no fixed end moment for AB, means AB and BA. And BC is having UDL over the entire span, so MF BC equal to, I will write it down the formula, minus WL square by 12, means minus 20 into L is 12 square by 12. So you will be getting minus 240 kilonewton meter. MFCB, same formula, but sign will be plus WL square by 12 equal to plus 240 kilonewton meter. One more span is remaining, CD, which has got point load at the center. So for point load, the formula is MFCD equal to minus WL by 8, which will be, W is the point load acting at the center, which will be minus 250 kilonewton meter. MFDC will be plus 250 kilonewton meter. And this is the very first step in case of MDM, moment distribution method. Second step in MDM is distribution factor table. By this table we are getting distribution factor for the members. So I will tell you the format of the table, how it is. Format of the table: first we have a joint, then member, relative stiffness, which is also a member stiffness factor, which is denoted by K. Okay. After this we have joint stiffness factor, summation of K. Then we have a distribution factor. We know the formula of distribution factor is K by summation of K. It is the ratio of member stiffness factor and joint stiffness factor. Now joint we have to consider, you see the problem, we have to consider a joint which has got two members or more than two members in case of distribution factor table. You see, A has got only one member, we don't have to take in the joint. B has got two members, similarly joint C has got two members, so we have to take joint B and joint C, we don't have to take A and D. The joint which has got two members or more than two members we have to take. Okay, so first I will take joint B. Joint B has got two members. Name the members, BA and BC. Okay, for BA find relative stiffness or member stiffness factor for BA. So whenever you are calculating member stiffness factor, you have to see what is the support condition of the far end. You see again, BA you need to see what is the support condition of the far end. If the far end is fixed, then member stiffness factor is 4 EI by L. By the way, EI is constant here. Okay, if the far end is hinged, far end is roller, then member stiffness factor is 3 EI by L. Remember. So here we have far end is fixed, it will be 4 EI by L. L is 12. So it will be EI by 3. BC also far end is C and it is intermediate support. Okay, and this intermediate support is treated as fixed support. So you see the far end is C, it is intermediate support and it will be treated as fixed support. Here also BC is the far end is fixed, so it will be 4 EI by L. L length of BC is 12 meter. EI is constant. So EI by 3. After completion of this, find joint stiffness factor of joint B, which is nothing but summation of member stiffness factor connected to joint B, means KBA plus KBC. Okay, KBA plus KBC, it will be 2 EI by 3. Now find distribution factor for BA and distribution factor for BC. Distribution factor of BA is member stiffness factor of BA, EI by 3, divided by joint stiffness factor of joint B, because BA is associated with joint B. So you will get 0.5. Similarly for BC, if you calculate, you will get 0.5. One more joint we have is joint C. Joint C has got two members, CB and CD. CB and CD. CB, you see far end is fixed, so it will be 4 EI, EI is constant by L. The length of CB is 12 meter. And CD, here also the far end is fixed. Okay, so it will be 4 EI. The length of CD is 8 meter. This will be EI by 3 and this will be EI by 2. Joint stiffness factor for joint C will be KCB plus KCD equal to 5 EI by 6. Distribution factor for CB will be 0.4 and distribution factor for CD will be 0.6. Third step we have here in the analysis of a continuous beam by moment distribution method. The third step is MDM table. So I will tell you the format in the table. So first we have a joint, then we have a member, okay, then distribution factor, FEM, fixed end moment. Okay, so see all the joints we have to take. Joint A has got only one member, AB. Then we have joint B. Joint B has got two members, BA, BC. Joint C also has got two members, CB and CD, and joint D has got only one member, DC. Distribution factor we don't have to write for AB and for DC. We can write distribution factor for a joint which has got two members or more than two members. Okay, so BA, distribution factor for BA 0.5, for BC it is 0.5, For CB we have calculated it is 0.4 and for CD it is 0.6. Don't have to write for this. FEM we have calculated for AB and for BA it is 0. For BC it is minus 240, CB plus 240, CD minus 250, DC plus 250. Now you see, after FEM we have a step by the name balance. In balance step we have to balance a joint, a particular joint. Okay. Now you see, joint B, the net moment at joint B is 0 minus 240. So what will be the net moment here? Net moment will be minus 240. Is it right? Net moment at joint B. In order to make it 0, in order to make it balance, okay, we have to apply plus 240 so that joint B is balanced. Okay, and joint B has got two members, BA and BC. So this 240 will be shared to BA and BC by distribution factor. So 50% will be resisted by BA and 50% will be resisted by BC. Okay, so we have to apply plus 240 kilonewton at joint B in order to balance this minus 240 kilonewton, so that the balancing is done. The net moment is 0 at B. So for BA, multiply it by 0.5 because distribution factor is 0.5. So you will be getting 120 for BA, 120 for BC, because distribution factor is 0.5, 50% shared of the resistance is taken by BA and 50% is taken by BC. Similarly, you see the net moment at joint C, 240 plus 240 minus 250. So the net moment at joint C is minus 10. Okay, so in order to balance it, we have to apply plus 10 kilonewton meter moment at joint C so that it get balanced, and this 10 is shared by CB and CD by distribution factor. Okay, plus 10. So 10 into 0.4, 4, 10 into 0.6, 6. So total comes to 10. Here you get minus 10, here you get plus 10. This is balanced. After balancing, after balance step, we have a step carryover factor. Carryover factor means when you apply moment, when you apply some moment, if the far end is fixed, half of the moment is developed at the far end. Okay, so 120 kilonewton meter you have applied at BA. So what is the far end? AB, and the far end is fixed. So we know the concept of carryover. If the far end is fixed, half of the moment is transferred to the far end. So here you will get 60 kilonewton meter. Okay, again BC, what is the far end? CB. BC, far end is C. Okay, and this C is intermediate support which will be treated as fixed support. So half of the moment is transferred to CB, 60. Again you see CB, at CB you have applied 4 kilonewton meter, CB, and what is the far end? BC. Again the far end is intermediate support which will be treated as fixed support. So here you will get 2 kilonewton meter. CD, at CD you have applied 6 kilonewton meter and the far end is DC. Okay, so half of the moment is transferred to the far end because far end is fixed. Again we need to balance. You see what is the net moment at joint B after carryover. What is the net moment at joint B? So net moment at joint B is 2. Okay, in order to balance it we have to apply -2, and that -2 is distributed to BA and BC by distribution factor. -2 into 0.5 -1, -2 into 0.5 -1. And you see net moment at joint C is 60. In order to balance it we have to apply -60, and that -60 is distributed to CB and CD by distribution factor. -60 into 0.4 -60 into 0.4 you will get -24, -60 into 0.6 you will get -36. So again you have carryover. I don't have to explain you. -0.5 -0.5 -12 -18. Again balance. Okay, -12 apply +12, distribute it to B and BC, 6 -0.5 apply +0.5, 0.2 0.3. Okay, again we have a carryover 3 0.1 0.15. Again one more balance 0.1 0.005. okay, sorry, 0.05 -0.05 -1.2 -1.8. okay, so if in the balance if we get something like 0.05 you can stop at that point. Okay, it will be better if you stop at balance. You can also stop at carryover, but it will be better. You will get some accurate result if you stop at balance. Now you see you add up from FEM to the last point, you add up all the moments here. When you add you will get 62.5. this is your MAB. okay, you are adding BA. if you add from FEM to this point you will be getting 124.95. $124.95 for BA minus 124.95 for BC. For CB this will be your MBA, this will be MBC. For CB and CD you add up all this value from FEM. remember you will get here 281.5. this will be minus 281.5 MCB MCD. okay, MDC 235.15 MDC. Now we have to draw a bending moment diagram. I will tell you how to draw bending moment diagram. First you see the sign convention of bending moment diagram. When you are analyzing by displacement method, you have to see how to use the sign convention. There are different sign convention available in the reference book, so I will explain you what I am using. Take a member AB. For example, this is a member, this is datum. Okay, at A, minus will be above the datum, minus moment, negative moment will be above the datum, and positive moment will be below the datum. At right, positive moment will be above the datum and negative moment will be below the datum. And the sign convention is only for the end moments. End moments means MAB, MBA, MBC, MCB, like that. Okay. So first step, when you are drawing bending moment diagram, you have to draw the free moment diagram. I will draw the datum here. Okay, A, B, C and D. Okay. So first you have to draw free moment diagram, free bending moment. You know how to draw free moment diagram? Free moment diagram depends on the loading applied on the member. Okay, AB has no load, it will not have any free moment diagram. BC is having UDL over the entire span, so BC will have free moment diagram, which will be parabola, and the height will be WL square by 8. Okay, so you will get 360 kilonewton meter. CD has got point load at the center. Okay, so the free moment diagram will be a triangular, WL by 4. You will get this as 500 kilonewton meter. With regards to free moment, the positive moment will be above datum and the negative moment will be below datum. Okay, now we have to superimpose the end moments. Okay, whatever end moment we have calculated, we have to superimpose here. These are the end moments. So already given you the sign convention. This is my sign convention. Okay, this is my sign convention. MAB is positive. At left, positive moment will be below the datum. So 62.5 kilonewton will be below the datum. Okay. MBA at right it is positive. Positive will be above the datum, so it will be here. Okay, this is 124.95. Okay, come to BC. You see, B is at left, negative moment will be above datum. MBC is negative, it will be above the datum, so it will be the same point. It will be the same point because it is negative and it will be above datum. Okay, same point. MCB will be positive. It is positive, will be above the datum, so it will be here. I will just okay. This is 281.5. MCD negative. It is at the left of the span, negative, above datum, same point. MDC right of the span, it is positive, will be above the datum. 35 less. 235.15. Now see, with respect to end moments, if the end moment is below the datum, it will be treated as negative. If the end moments are below the datum, it will be treated as positive. If the end moments are above datum, it will be treated as negative. So this is negative, and this is positive. and this part is nullified. Okay, you can draw like this. This part is nullified. So whatever free moment is remained, it is positive moment. Here we have a negative moment. So this is bending moment diagram. Thank you for watching this video. Thank you very much.